everybody. Well, it's that time again, which means we are going to go back into Chem 140. Let me wind the music down here. What do we got on the agenda? Let's see. There's a quiz that was due yesterday. Tonight's last call for quiz number 2. Get that in by the deadline. It will close tonight at midnight. Make sure you get it in on time. Quiz number 3, which is units 4, 5, and 6. That is due next Monday, May 3rd. Get an extra day to do that, too, if you need. I think the next quiz, which is quiz 4, is... Let me check. I think it's unit 7 and 8, so that's not going to come up for a bit. Yeah, it's unit 7 and 8. Oh, no! Oh, no, I can hear her in the background. Yeah, it's you. Maya wants to say hi. Come here. Come here. Come here. What would you like to let the students know? Okay. I'll make sure that they heard that. Okay. Hopefully you heard that. She says, Professor West is not petting me right now, although he is the second. He would much rather spend his time with you. How dare you? I think Maya's just jealous. Where'd you go? Where are you? Oh, you left. Okay. Well, she just wanted to say hi for 2 seconds. I guess that was it. We already talked about lab number 2, I realize. So if you have, if you missed the lab number 2 stuff and you're looking for it, look on Tuesday's lecture last week. We talked about how to make a graph. Because I was setting it all up today, and I was like, wait a second. I've already shown these guys how to make a graph. Did I already do this? And so I went back and looked, and yeah, we had already done it. So we don't have to do that this week. So lab number 2 is actually now available on Canvas as an assignment. I mean, you could always access the lab materials and stuff, and so maybe you've already worked on or even finished lab number 2. Lab number 2 is all about density. There's a lot of calculations in there. Be very meticulous with your sig figs. And when you're finished, upload that to Canvas. It is due next week. I should really put that on the bottom here. Hold on, let me add that. I gotta go back to the title card to do that, though. So, let's see here. Hopefully that didn't, like, crash through everything. Okay, cool. So yeah, lab number 2 will be due next week. Next week's also an exam. There's an exam at the very end of the week on Friday. So you'll notice that there are quite a few things that are due next week. Quite a few being 2. But don't get overwhelmed by that. Make sure that you're working on stuff up until then. Maybe do the stuff early. Don't leave it till the last minute, because then you'll be like, oh shit, when do I study? And time will be up and the exam will be there. So be careful. Be careful with your time. All right. Unit 7 is all about atoms and molecules and particles and defining them and describing them and all sorts of stuff. So we're going to finally officially describe what a proton is. Yay. Right? Like, it's about frickin' time, right? Well, here we go. Okay, so first we got to describe what an atom is. So I'm going to give you a sheet of copper as a thought experiment. Boop, there's my sheet of copper. And then what I'm going to ask you to do is cut this in half. Boop. There you go. And then I'm going to ask you to do that over and over and over and over and over again. Boop, 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 boop. Now, eventually, at some point, you will get to the smallest piece of matter that you can still call copper. If you cut that in half, what you have is no longer copper. You have the pieces that make up the copper particle. That tiniest particle is what we're going to call an atom. An atom is the smallest individual unit that has the properties of one of the elements on the periodic table. Now, copper is just the one that I used for my example, but you could do this experiment with any other substance, although it'd be a little bit more difficult if you picked a gas, for example. All right, so now that we have this idea conceptually what an atom is, we can talk a little bit in more detail about how atoms behave and how they're arranged and stuff like that. Yeah, Maya is adorable. She's not small. I mean, so she used to be really overweight when I got Maya. She was like 14 pounds, and now she weighs like 9. And all I've really done is just feed her regularly. I don't know what her previous owners did so that she became so big. But she has bad hips, so she's sort of just like, she's not very active. She follows me around like a shadow. Like, I'll go anywhere, and then Maya's there, and she's adorable. Oops, I didn't mean to click through that screen. The other cat doesn't say anything on the mic. He doesn't like the microphone. All right, what are we going to talk about for atoms? Atoms are super, super small. One single atom of gold, which you can see in this picture here. So using an electron microscope, we can zoom in really, really close. And so each of these little circles that you can see here, I'm not circling each individual circle in a sequence. I'm sort of skipping over them. Each of these is an atom zoomed super far in. As far in as we can really reasonably get. Now, the pattern that you see, like the stripes, the atoms themselves don't actually exhibit stripes. In fact, you should just see like what looks like, I guess my best description of it would be like a honeycomb of just atoms across the surface here. Those stripes are probably due to diffraction of the electrons or the light that is used to make this observation. And so you get areas of high resolution and areas of poor resolution. These numbers at the bottom are just intended to let you realize how tiny these things are. You would need 3 times 10 to the 21 atoms to equal the mass of a paperclip. So that would be 3 with 21 zeros behind it, which is an enormous number. You need that many gold atoms to make a gold paperclip with mass 1 gram. And it'd be a really small paperclip anyway, because gold is extremely heavy relative to other atoms. So like aluminum, which is what paperclips are probably made out of, is much, much, much lighter, and so it would be much, much, much bigger. All right. Now, in terms of what atoms have in their contents, like what is the stuff inside the atom, we're not really going to discuss like how these things were discovered in this class. We're going to do that in 161 when we talk about like the gold foil experiment and the Millikan's oil drop experiment, cathode ray tube, stuff like that. For now, what we're going to do is we're just going to illustrate a picture. The nucleus is the solid part of an atom. We're going to define that in a little bit more detail in a little bit. Its diameter is roughly 10 to the minus 15 meters, like a femtometer. That's super, super tiny. Outside of the nucleus is this space. And the space is where electrons roam. And when I say roam, what I mean is, if this is my electron right here, it doesn't go in a pattern like this, like a planet would go around the sun. We'll describe a little bit more why that is later. But the path that an electron takes is very chaotic. And it tends to go around the nucleus at a reasonable distance. But you can see sometimes it gets closer, sometimes it gets further away. But on average, it's in this circular region that I've defined. That's called the electron cloud. The electron cloud is where electrons basically exist. Now, because the electron cloud is 10 to the minus 10 meters, which is about 100,000 times larger than the nucleus, by volume, that means that 99.99% of the volume is actually empty space. Now, obviously, my diagram is not to scale, because there's no way I could fit something here and then have a 10,000 times or 100,000 times larger image of this. So if I said that this mark on my screen here was 1 centimeter long, then that would put the edge of the electron cloud 100,000 centimeters away. which would be roughly 1,000 meters or a kilometer away. Now, obviously, my monitor is not a kilometer large, and a kilometer is quite a distance. So, from where I live, the edge of the Electron Cloud is probably passing through something like, say, Fred Meyer. I live next to Boeing, and there's a Fred Meyer nearby, so it's down the road. Now, on the periodic table, and I believe that I've linked p-table a bunch of times in this class, but if I haven't, here it is. Let's go get p-table. I don't know which classes I haven't linked p-table. Obviously, you're going to want to keep p-table handy here because it is handy as a resource, but we're going to, oh, excuse me, we're going to use it a lot. Oh, that's not super useful. Hold on. I don't need the ads and stuff at the bottom here. We don't really need all of the thermodynamic data. Although seeing the thing in the top left corner of what I have selected is kind of useful. So this is what you'll see if you clicked on p-table. Whatever element my cursor highlights will appear in the top left. We're talking about gold right now, so I'll just click on gold. There we go. And I can click on it and it will stay there. So we're going to learn what these numbers and things mean in the periodic table in Unit 7 and in Unit 8. Unit 8 is going to be more about, like, what is column 1 called? What is column 2? What is column 8 called? What are these different regions that are highlighting? That is like some game show board. We're gonna cover all that in these next few chapters. But on the periodic table are 118 different elements that we are aware of. And by when I say aware of, I mean we have synthesized them and detected them to a 5 sigma degree of certainty. 5 sigma basically means that there's like a 1 in 3 million chance that the data that we acquired to confirm that this is indeed the element we think it is a statistical fluke. And if we can get the odds of that fluke happening down to 1 in 3 million, we're essentially certain that what we are looking for actually exists. You obviously do not need to know all of the names of the atoms because you have a periodic table handy, and the periodic table has all the names on it. So feel free to reference this whenever you need to, and be particularly careful about any elements that have similar sounding names. So, like, potassium is not P. That's phosphorus. So, oops, there we go. There's phosphorus over there. Potassium's actually over here, calcium. So, we talked about a few of those names at the end of chapter 6 yesterday. So, just be mindful. Now, all atoms of a given element are identical in terms of their chemistry. Now, I'm saying chemistry specifically because in terms of their physics, that's not necessarily true. And we'll learn that in a second when we talk about isotopes. That means that you can rely on all atoms to have the same behavior in the same situation. So, for instance, if one sodium atom explodes with one water, all sodium atoms will, because they're all chemically identical. When you do a reaction to combine different elements together, you get a compound, and each combination gives you some substance that has its own unique traits and properties. For instance, water and hydrogen peroxide, as you can see the formulas below, have the same atoms in them, H's and O's. H by itself does one thing, O by itself does another thing, but when you combine them in different ways, you get even more unique results. Water is not the same as H or O, neither is it the same as hydrogen peroxide. In fact, if you drink hydrogen peroxide, you'll regret it because you'll get a stomach ache, and it'll start bubbling and fizzing in a very bad way. But H2O is quite stable and is refreshing, and also necessary for life, so stay hydrated, drink water. Every hour, spend a minute or two just drinking water. What is wrong with you people? Just drink water. Now, when you do a reaction in chemistry, I should be specific, we are going to be changing around how atoms are interacting with each other. And so when I say interacting, what I mean is bonding. We're going to talk about bonding in Chapter 9 after exam number 1. But for now, what we care about is simply how do we describe these entities in a pictorial sense, in a symbolic sense, so that we can then play with them and draw structures and things like that and do all sorts of neat things. However, whenever we do these reactions, we are going to work on this assumption. Atoms are indestructible. You cannot break them into pieces because otherwise we would not be doing a chemical reaction. All chemical reactions, generally speaking, occur at what I would call low energy. Now, obviously, like setting something on fire is a chemical reaction. You might not think, oh, that's not low energy at all. You could burn a house down with that. That's a lot of energy. Or you could power an aircraft carrier with fuel. That's a lot of energy. But relative to the amount of energy per molecule interaction, chemical reactions are far lower energy than, say, a nuclear reaction. So combining two hydrogens to get a helium in the core of the sun produces way more energy than combusting hydrogen and oxygen, for example. I'm just going to put the pictures up before we talk about things. In units, I want to say 9 and 10, we're going to deal with two different compounds. I want to say ionic is unit 9 and covalent is unit 10, but we've changed the chapter numbers for 160 or 141. So I always get this confused. I will eventually learn this by memory, but for now, one of the chapters we're going to do coming up is going to be ionic compounds. Ionic compounds are crystal lattice sort structures like this that I'm highlighting over here, and are formed when you have different charges. Oops, that's the wrong color. They form when different charges, that's the wrong pen, my goodness, there we go, interact with each other. So opposite charges will attract to each other, and then they will stick, kind of like miniature magnets. This is called electrostatics. And then what will happen is that these will stick to each other, but they also stick in all directions. And so I will get a bunch of positives that will attract around this negative, and then each positive will then get negatives that attract around it, and so on and so forth, until you get something that looks like this. So that the simplest pattern that we have right there, sodium chloride, is just this cubic arrangement where you essentially have repeating arrays of alternating sodium and chloride ions in all directions, essentially forever, until you reach the end of the lattice. So all of those ions are stuck together. We don't really call it a molecule. We're going to call it a formula unit. We'll describe that later. Molecular compounds are actually molecules. And what a molecule is an individual collection of atoms that exist independently. So these things that I'm circling here are all independent. They are not stuck to each other, and so they can move freely. We see molecular compounds more often in things like liquids or gases. Like the air that you're breathing is all a bunch of molecules. Ionic compounds, though, tend to be very, very regular and stuck together because the forces that hold each individual particle together are very strong. We're going to describe this in more detail in later chapters. We're going to talk about bonding and about why it's different, and then we're going to make formulas out of stuff and things like that. Now, molecular matter is very common. It turns out that atomic matter is the exception here. Most matter does not exist in the atomic state. Noble gases do. Helium, neon, argon, krypton, xenon, they just bounce around by themselves as independent little particles. So if I described a gas of one of these things, it just looked kind of like this. Here's my particles. They're all independent, and they're all moving in any which way, and maybe this is the boundary of my container. But if I had oxygen molecules, for example, oxygen exists in pairs, and so that would look like this. They're not really bigger. They're roughly the same size as atomic matter. They're just two of them together. And then each of these would move around independently or bounce off of each other or whatever. But those two atoms would be joined together. And they're joined together through a bond. Now, what matter exists in the molecular form that's common? I think that we show that on the... Do we show that on the next slide? Where's the silly 7? We may have already talked about that. Just in case we haven't, we're going to get to that later, but H2, N2, O2, F2, Cl2, Br2, I2. So these are really common molecules that occur, those 7 that I've written right there. Then there's also things like water, CO2, sugars, things like that. On the bottom, I have some pictures that illustrate various molecules that you're not likely to encounter. Some of these. Like we're not going to talk about sulfur or phosphorus very much, but they exist in molecular forms. When we draw pictures of them in this manner, we use different colors to indicate different elements. There are some common colors that are assigned. So, for example, hydrogen's always the white sphere, carbon's always the black sphere, oxygen's always the red sphere, and so on and so forth. As we hit more of those, we will describe them so you know the convention. But it's not worth committing those to memory. You'll just learn that eventually. Next, we have a few terms that we can use to describe molecules in more detail. So the first term that we're going to use is a term that is assigned to a molecule to count the number of atoms that are in the molecule. Note that even though we have only one atom on the left example, and that would be atomic, we're still going to use it for this example. And so what we say is we say a number prefix in front of the word atomic to basically count the atoms. So we've got 1, 2, and then 3. So we'll go monatomic, mono being 1, diatomic, di being 2, and triatomic being 3. Now, other words are used. You can do tetra, penta, hexa, hepta, etc. And just count up how many atoms you want that way. A more common convention is to say, oh, something is polyatomic if there's more than 3 atoms. So 4 or greater. Just apply the word polyatomic and that's good. Many compounds that we work with are going to be very few atoms. But we will work with things up to 6 or 7 is common enough for a molecule or an ionic formula unit or so on. The second label that we're going to use describes heterogeneity of the molecule. Are all of the molecule or all of the elements in the molecule the same? Or are they different? Is there one type of element or are there multiple types of elements? So in these pictures here on the left, I just have one type of element because they're both the same color. That would be oxygen or O2. On the right, though, I have carbon dioxide, CO2. And you can see because there's different colors, there's different atoms in there and different elements. So we'll apply the prefixes homo and hetero, just like we did for homogeneous and heterogeneous. Homo meaning same and hetero meaning different. In a homoatomic molecule, all of the atoms are the same element. There's only one type. In a heteroatomic molecule, you have different types, and that's 2 or more. So something with only 2 types would be heteroatomic, something with 6 different types would be heteroatomic. So heteroatomic, obviously, the more common occurrence. You're going to ascribe one name from each of these 2 categories. So one of the types of atoms names, and then one of the number of atoms names for any given molecule. So for example, this molecule right here, oops, wrong pen. This right here would be homoatomic, because only one element, and diatomic, because there are 1, 2 atoms. This one right here would be heteroatomic, because 2 different elements, 1, 2. And then triatomic, because 3 different atoms. Easy enough, right? Let's just have you do the examples. Oops. There you go. So, just as a heads up, so this line right here, these are supposed to be dividers. These are 6 different examples. What I want you to do is categorize each of the 6 molecules you see here as either monatomic, diatomic, triatomic, polyatomic, and so you need one from the yellow group here, and one from the whatever color I'm about to pick, blue group. Okay? So on the top, I have the picture versions. On the bottom, I have formula versions, because we're not going to work with pictures all the time, because sometimes that's tedious to typeset or whatever. So you could, but the same principle still applies. Okay? So assign the correct terms for each molecule, and then type your answer in the chat. We'll go over the answers together in about 4 minutes or so. One more minute, we'll go over the answers. All right, so what we're going to do is first I got to get the right pen. That's the arrow tool. What am I doing? There we go. We're going to assign a term to each of these molecules. So the first one, there's 3 of them, so we're going to call it triatomic. Well, if I can spell it right. And they're all the same element, so I'm going to call this homoatomic. For the second one, I'm going to say, okay, well, there's 1, 2, 3, 4, 5. I could say pentatomic, but polyatomic is also good. And there are 2 different elements. There's the red element and the blue element, so we'll call it heteroatomic. Over here, there's just 1 atom. It's monatomic. And anything monatomic can only be homoatomic. So putting this label is not really super useful. Oh, sorry, I'm itching my beard here. But we'll apply just to be complete here. Down here at the bottom for benzene here, C6H6, there are 12 total atoms. So I'm going to call that polyatomic. And there are 2 different elements, so we'll call it heteroatomic. For bromine over here, there's 2 atoms, so we'll call it diatomic. And they're the same element, so homoatomic. And then finally over here, we've got triatomic, because there's 1 beryllium and 2 chlorides. And because there's 2 different elements, that's heteroatomic. There you go, that's the first example done. Any questions, let me know. All right, let's keep going. Let's talk about the pieces of the atom. Because there are little parts of the atom that are going to be very important to this class and future chemistry classes, so let's understand them in a little bit more detail. Now, remember my diagram is exaggerated. The nucleus is nowhere near that big relative to the electron cloud. But the nucleus is the region in the center. And I don't want to do that color because that's going to changes the color of everything under it. I don't really have a... Oh, you know what I could do? I could do this. That's not the right pen. I swear, this interface sometimes does not cooperate. There we go. We'll do this. This part. The part that I lightly colored over in gray, that's the nucleus. The nucleus is the small, solid, dense part of the center of the atom. 99.99% of all of the matter in an atom is in the nucleus. The electrons make up a very small amount of mass relative to the nucleus. Now, this is a cartoon of the atom. However, it's not a very good representation. And the reason for this is the following. So I'm going to put the caricature up here. But we're going to draw what's actually going on around an atom. And we're going to use an analogy here. So the analogy that I'm going to use is the solar system. So here's the sun. And here's the Earth. And the Earth goes around the sun in an elliptical orbit that's very regular. And we can predict this orbit to a high degree of precision using tools, and we've built a calendar around it and all sorts of things. So this is a very regular system. There are other things acting on the system, but principally, the one force that is keeping the Earth in check here is gravity. The gravitational attraction between the sun and the Earth. Now, the sun does not pull the Earth into its core and then we all burn in a fiery explosion. That's because the Earth has momentum. If gravity were to stop all of a sudden, the Earth would just go sailing off in some direction, like so. Thankfully, that doesn't happen. And the end result is that we have this elliptical trajectory that's very regular. Now, our orbit is very regular because there is not another entity nearby that is exerting a force of equal magnitude. So even though Jupiter, way over here, is very large and the Earth is attracted to Jupiter, it is by no means attracted as much as it is to the Sun. And so its orbit doesn't really change appreciably. So you get a regular pattern. In an atom, it's very, very different. I'm going to put 2 protons in the center here. And then I'm going to put 2 electrons here. Now, if these went around in a regular pattern, they would have to stay very far apart from each other because electrons want to repel from each other. They're still attracted to the nucleus, but they don't want anything to do with each other. So if this electron ends up getting too close right here, for example, then what ends up happening is this guy's going to suddenly start moving in this direction, and this guy's going to start moving in this direction. And we're going to not have a circular path. We're going to instead, oops, that's the wrong button. We're going to instead have a path that kind of goes like this, based on where the other electrons are. And the other electron is going to have that sort of thing going on too. So we get a very chaotic path. And so instead of drawing out the path, because 1, it's very difficult to predict this when you have more than 1 electron, 2 or 3 or 20 or whatever, it just gets so chaotic so quickly because there's so many forces acting in so many directions. There's too many variables to solve that. So instead what we do is we just say, okay, here's my nucleus, and I'll put my protons back in the center. And then along the outside somewhere is where my electrons live. And they're just somewhere in the electron cloud. So you're going to see the diagram of electrons on these constrained rings, and just know that that's a model and it's not a good one. However, it does have some uses to it for describing how many electrons can go at what distance from the nucleus and so on. So that's why it has some use. Now, obviously the diagram is exaggerated, so that's great. What are the parts of the nucleus? In the nucleus, we have 2 nucleons that we care about, and here they are. So we got the proton and the neutron. Protons are big and bulky and have a charge. The charge is positive. Neutrons are big and bulky but have no charge associated with them. They are neutral. Now, neutrons actually attract to protons through a very interesting phenomenon called the strong nuclear force. This is nuclear physics, and I don't really have a good explanation other than if you put a proton and a neutron really, really close to each other, they attract. And that attraction is stronger than the repulsion of neighboring protons pushing each other apart. So neutrons are kind of like nuclear glue. They hold the nucleus together and keep all of the protons from repelling each other. If you don't have enough neutrons, the protons push apart and the atom disintegrates, and you get fission. Basically, your atom splits into pieces. The same problem occurs though if you have too many neutrons. Neutrons need to stick to protons. They don't really stick to other neutrons, and so if you have too many neutrons in the nucleus, you get other weird, fascinating things. For instance, a neutron can spontaneously turn into a proton and an electron. And then the number of protons in the nucleus changes if you have too many neutrons. That's nuclear chemistry. We don't really talk about that terribly much in this class, unfortunately. But we'll cover it a little bit in 163. I think it's personally really interesting. I took a class on nuclear chemistry, and there's very little to basic nuclear chemistry. Like, you could fill a small textbook with it, not like your general chem textbook. Now, what about on the outside here? We have the electron. The electron is very, very small in terms of mass. Electrons are teeny, 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 tiny. They're like 1/2000th of the mass of a proton. What makes electrons important is that they contain a charge too, and their charge is the opposite of that of the proton. They have a minus charge. The signs we've assigned charges are arbitrary. We could have called them like square and circle, or up and down, or whatever. So plus and minus are arbitrary. They don't have anything to do with math, which is unfortunate because we also use the symbols for math. But we will actually manipulate them as if they were math when we're adding charges together. So like +1 for a proton and -1 for an electron. The total overall charge would be 0. And again, anything with like charges will repel, and opposite charges attract. That's a fundamental physics interaction. In fact, that interaction right there, what I've highlighted in blue on the left there, that's all of chemistry, it turns out. Chemistry is entirely the consequence of electrostatics, which is cool. Doesn't make it easy, unfortunately. Now, in an atom, the total charge present is always 0. Atoms are electrically neutral. The number of protons and electrons must be equal. If you don't have an equal number of protons and electrons, you get something different. We're going to talk about that in the next section coming up, probably after the break here. Most atoms are content to be neutral, but many atoms have an impetus to either gain or remove electrons. We're going to manipulate the number of electrons as opposed to manipulating the nucleus. The nucleus is very difficult to change. That's because it's in the center and it's tiny and it's dense, and knocking something out of there would require tremendous energy. Electrons, on the other hand, are tiny. They're very far from the nucleus, so you could scoop one away. You could bonk them off with light. All sorts of things will affect electrons. And that's where chemistry comes in. Chemistry is actually just electrons. We're going to talk about ions, which are any substance that has a different number of protons and electrons, in the next section. Now, if I pull out the periodic table again, I got to make sure it's still captured here. Now it wants to capture PowerPoint. Why did you do that? Oh, because I minimized the window. Yeah, it doesn't know where that is anymore. It's invisible. It's miniature. Okay. Now it's going to capture this, which is just my... Hey, you haven't clicked on this tab for a second, so let me wake it up. There's our periodic table again. You can see that every atom that I have right here, I'm just going to pick one right here. Up in the top left corner is a giant integer. We have a symbol, the name of it, and then this decimal down at the bottom. Don't worry about this on the right. We're going to talk about these numbers in 161. But this number at the top left is very important. This is what's called the atomic number. The atomic number is, by definition, the number of protons an atom has. That's how we identify stuff. If you have 11 protons, you are sodium. If you have 40 protons, you are... I gotta look at the periodic table. I just picked a number. 40 is zirconium. 6 protons is carbon. 10 is neon, and so on and so forth. We have named every species all the way up to 118 protons. Oops. So, nothing really special about that, but that is kind of a key point. We define atoms based on protons because, again, it's hard to change the number of protons. Now, what about neutrons and electrons and so on and so forth? Well, we can be more descriptive by writing a term symbol for these things. We do not use the numbers on the periodic table for this particular action, except for the atomic number. This is really the only number that we care about, and we also care about the symbol. So ignore the bottom number for now. We'll get to what that means later on today. So let's look at these symbols in a little more detail. So first, we're going to define the atomic number as this variable here, Z. Z is used in many applications. We're going to use Z a lot in 161. You see it a lot in physics as well. So Z is just the number of protons. A is another number that we're going to be assigning. A is the number of protons and the number of neutrons added together. It's called the mass number. We call it the mass number because it's the mass of the atom, more or less. We're going to use these two things together to describe various atoms, because I'm going to give you a scenario, like, here's a particle that has this many protons and neutrons. Write a symbol describing it. Now, because all of our atoms are neutral, the number of protons and electrons will be the same. So if you know what Z is for protons, you also know what the number of electrons is. Ions will change that up a bit. We'll do that next after this. Last thing I want to mention is that the mass number is not the atomic mass in the periodic table. So this number right here, down at the bottom, I'm going to write this out explicitly because people always mess this up. This is not A. Okay, that's something totally different. What it is, though, will be close to A. And that's where people get confused. So it's not the mass number at the bottom. All right. Give me a second. We might be due for a break before we do this, because I don't want to start an exercise and then have you working through the break. Oh, no, there's only one slide after this, so it's just this. Okay, so let's do this. We'll have you do the examples, and then we'll take a break. All right. Now, what we're going to do is we're going to describe something called isotopic notation. I call it ZAE, or ZAE notation, just for short because it's catchy, but nobody else does. Here's how you write an isotopic notation symbol for any given element with any number of protons or neutrons as described. So the first thing you want to do, whatever element you are looking at, you want to get rid of this symbol right here, this curly bracket Z, and replace it with whatever symbol you're looking at. So if I was looking at carbon, I would just do that. If I was looking at calcium, I would do that, and so on and so forth. All the symbols are on the periodic table, so just reference the periodic table for whatever element you're using. In front of your symbol that you just wrote, you're going to write a subscript, and that subscript's going to be Z. Z and the symbol are linked together. For instance, if I have carbon here, I shouldn't use carbon because that's going to be my little example here. For example, if I have iron here, I can never write any number other than 26 because iron is, by definition, the species that has 26 protons. That's its atomic number. Also, if I had cobalt here, I can't write any number other than 27. Cobalt is, it's iron with an extra proton. That's cobalt. So those two are going to be presented together, and a lot of the times Z is omitted because it's redundant. But for our purposes, we're going to include Z, just to get in the practice of doing that. The mass number A is written as a superscript before the symbol that you wrote. Remember that that's the number of protons and neutrons added together. And there you go, you're all set. So that's isotopic notation. You're going to get a symbol with a number before it on the bottom and a before it on the top. So as a really simple example, I'm going to give you this sulfur atom. I thought it was carbon, actually, so I guess I changed the example. I'm going to give you this sulfur atom, and it has 16 protons and 17 neutrons in it. So we want to describe that by writing an isotopic notation symbol. Well, the atomic number is 16 because it's sulfur, so I'm going to put 16 down here. And then the number of protons, oops, that's neutrons. No, protons plus neutrons is the mass number, A. Well, 16 plus 17 is 33, so I would write that up here. And there you go, that's the symbol. And that's it, you just do that. Now, in order for me to make it more challenging, I'm going to like try to obfuscate what I'm telling you. So I might tell you like write a symbol for an atom with the same number of protons and neutrons, and A is 42 or something like that. So you'll see that on the screen. I've made 4 situations where I'm trying to hide the information to make it more. You have to think about it more. So what I want you to do is write the isotopic notation symbol for each of these 4 atoms. Typing it into Google or typing it into the YouTube chat is actually very difficult. Do the best you can. Let me know when you're done, and we'll go over the answers in just a second. One more minute, we'll go over the answers. All right, let's do these. We'll take our break. So, an atom with 25 protons, boop, and 27 neutrons. So 25 plus 27 is 52. Boop. And then we got to find which element is 25 on the periodic table, and that is manganese. There we go. For the second one, I just gave you Z and A outright, so you just add them right there. And then you just got to go find element 37, and that's rubidium. Be careful, you don't want to add these two together. An atom where the same number of protons and neutrons, with the same number of protons and neutrons, where A equals 36. So if A equals 36 and half is protons and half is neutrons, that must be this, right? So I would write Z, and then I would write A, and then I find element 18, and that's argon. And then one fewer neutron than protons, and A is 19. So I have to have something and one fewer than that, right? So you could do this intuitively, and you'd say, oh, it's 10 plus 9. Or you could just you could do algebra. So the atomic number must be 10, and the mass number must be 19, and so that's neon. You can do a lot with algebra. Just in case you were sitting there like, how the heck do I puzzle that out? I'll make it an equation. And then you can just solve for it. All right, when we come back from the break, we'll talk about ions. So we'll see you for that. Oh, once I find the music. Where is my music? There it is. We'll just click on one. Oh, so close. Alright, we'll wind this down. I realized I was using the same music again. And I'm like, whatever, I like that song a lot. We'll just play Cygnus. Twice in a week. Alright, where are we at now? Oh, we're doing ions, that's right. Okay, so let's ionize. Alright, what's an ion? Ions are just different numbers of protons and electrons around the atom. And so we get very interesting effects because if you have different numbers of protons and neutrons, some amount of charge remains. And that creates interesting observations that govern pretty much how all reactions occur. So the basics are on the screen here. Opposite charges attract, like charges repel. The total charge on an atom is always 0 because the number of protons and electrons are the same. We already know all of that. Now, because electrons are going really fast on the outside, they don't bonk into the nucleus and stick there. That also means that they are ripe for picking. So you can either grab one and then you would have a net positive charge, or maybe you bonk into another molecule that has electrons and you take one of theirs. And then now it's floating around your nucleus, and now you have a net negative charge. In either case, you're going to end up with what's called an ion. An ion is any sort of entity, or particle, I should say, that does not have the same number of protons and electrons. The numbers are just different, sorry. We're going to assign 2 words to describe 2 different situations. If you have more electrons than protons, you would have a net negative charge, and the word we use for that is called anion. The an part is where you see things like anode for batteries and stuff. So the anode is the negative end of the battery, where the electrons come from. It's the negative source. The cation is when you have less electrons than protons, and that's where you get the term cathode. The cathode is where the electrons go. They go towards the positive terminal. The way that I remember these words is that if you write the word cation, and I'm spacing out the letters purposely here, I'm going to get rid of this T here, and I'm going to put the charge that it represents. And it still looks like the word cation, right? Because cation is positive. The other way that you can remember it, and you can't see me doing this, but I'm waving my right arm up and down like I'm one of those lucky cat statues that you see. I don't know, in like anime and stuff like that. That's really where I see them the most. I'm doing that, and then I would say, cats have paws, positive. And then I would give a really, really stupid grin because I'm imitating another instructor who likes to do that one. So whatever way helps you remember that the cation is positive and the anion is negative. Because I'm going to use the words cation and anion a lot in this class. Now, a lot of beginning students make mistakes when they're trying to calculate charge. And the reason for that is because if you subtract electrons, you end up with a positive number. But you would think, oh, I'm subtracting something. Why isn't it negative? Well, if my charge is 0 and I take away 2 electrons, remember electrons are negative, that's like doing this, right? So the charge would be positive from removing 2 electrons. So since you're dealing with negative numbers when you're adding and subtracting them, just treat it like that. Subtracting an electron is like subtracting -1. You get a positive number. Adding a -1 would give you a negative number. So adding electrons gives you a negative charge. So just be careful when you're sitting down and doing a problem where you're adding or removing electrons. And note, did I go the correct direction? And eventually you'll do it intuitively. But at the start, it's really easy to accidentally flip them. So be careful. So for this example, I'm going to remove an electron from sodium. Removing an electron makes a positive charge. There are more protons than electrons. So if I wrote something like this, so number of protons, and number, I'll put the number sign here, I guess. Number of electrons. So regular old sodium would have 11 of each. Sodium cation has 11 protons still. It has to have 11 because it's still sodium. But now it only has 10 electrons. And so the difference in charge would be, so if I made another one here, charge, 11 and 11 would be 0, because this is positive and this would be negative. This is positive, this would be negative. And I could just sum the numbers together. When you write a charge, you put it as a superscript after the symbol. If there's only one, the convention is just to write the symbol. If there's more than one, so like if I did this for calcium and I took away 2 electrons, you put the number first and then the symbol. Sometimes you can circle the symbol just to make it clear. I like to circle it. You don't have to do that. That's not a convention. But a lot of texts will do that. Just so you don't like accidentally interpret like the stray mark or whatever. Make sure you put the number before the symbol. In Canvas, it will be very specific, and it'll actually say put the number before the symbol. If you do it in the opposite order, Canvas won't know what you're trying to do, and it may mark your answer wrong. All right, so let's clear that. We'll put the answer on the screen there. All right, let's do the same thing for chlorine. Here's my chlorine atom. I'm going to give it an electron. Electrons are negative, so there you go. And pictorially, that looks like this. You'll notice that my picture here, the electron cloud changes shape when the number of electrons changes. If there are fewer electrons, the electron cloud shrinks. If there's more electrons, the electron cloud grows. That makes sense, because if there's more electrons, then there's a bigger space that they all inhabit. And if there's smaller, or if there's fewer, the space they inhabit is smaller. We're going to talk about that in more detail in 161. You don't need to worry about the size of the electron cloud, because that's not going to be relevant for anything we do in this course. In 161, it will matter a lot, but in 140, we're just setting up the groundwork for 161. So that's more of quantum mechanics. We'll get to that later. And again, charges are superscripts. Put them in the right spot. Now, some ions are very stable relative to their neutral atoms. For example, when we put sodium in water, you saw this on the first day. We threw all these elements in water on video, and we got all these pretty flames and explosions, and it was fun. But if you put sodium ion in water, nothing happens. There's no explosions. In fact, all it does is make the water salty. Table salt contains sodium plus cation, and you could go eat that. In fact, you probably eat it all the time. I certainly do. But you don't explode every time you pour salt on your food, and neither does your food or anything around you, because you're not putting sodium on there. So there's a very big difference between this and this in terms of chemistry. And we're going to explain that later on too. Now, somebody actually linked me this video about bananas and potassium. Was it in 140 or was it 161? I'm going to go quickly look at that. Did we get all the cool videos in 161, or did you guys send me that? I don't remember. I don't see it right away, unfortunately. Yeah, I don't know. But it showed how you can get... Oh, here it is. Potassium from bananas. So I'm actually going to link this video because this is really cool. So if you want to see how hard it is to get potassium metal out of bananas, you can watch this video later on. Don't watch it right now, obviously. But just put that in your browser and watch it later if you want. Potassium in bananas is this one right here. It's the ionic form. Metallic potassium with all of its electrons is very tedious to acquire and get out of bananas. And if you watch that video, it's like 20 minutes of this guy doing various experiments to get all of the other crap out of the banana and leave just like potassium ions, then precipitating that, then removing the precipitated ions that he had there, and then reducing it to potassium so that it's a metal. And then he shapes the metal into the shape of a banana and throws it in a pond, which then explodes, which is fun. So there you go. That's the 4-minute or the 4-second version of the 20-minute video. But suffice it to say is that ions tend to be more stable than atomic matter for particular elements, of which the elements in the first column are one of those. Oh, the knives guy. The knives guy's really cool. Yeah, it's a very long process. I mean, making a knife out of anything is a long process, but if your knife is made out of Jell-O, it's especially long. All right. So for our purposes for this exercise, what we're going to be doing is just predicting ions and giving them a charge. And then we're going to go into this in a lot more detail in Chapter 9. So if I want to give nitrogen 3 atoms, what ion would I form? Well, if I'm going to give it 3 electrons... Did I say 3 atoms? When I give nitrogen 3 electrons, it would look like this. Easy enough. If I want to make calcium and remove 2 electrons, I would just take away 2 electrons. It would have 2 extra protons. That's the overall charge. Boop, there you go. Easy as that. Now, what if you're trying to count them from an ion that's already shown? In this case, what I would do is I would just make a table. So number of protons, number of electrons, and then charge. So if I start with a neutral one, and I look at the periodic table, I see that there are 26 protons in iron. Well, if it's neutral, it must have the same number of electrons. And its overall charge would be 0 because, again, it's neutral. Now I'm going to make it positive 2. How do I do that? Well, if the overall charge is plus 2, I need to have 2 fewer electrons right here. So this would be what is in an iron 2 plus atom, or ion, I should say. And I lost the cursor. There it is. All right, so I have more exercises for you to do. Here you go. Here's a giant table. What I want you to do is you're going to write the isotopic notation symbol for each of these species, and you'll notice that I have included the number of protons and electrons. I want you to put the charge right here. Okay? So since charge can be labeled... Actually, let me do a different color so it stands out a little more. There you go. So notice how I've included the charges on my isotopic notation symbol. Put whatever charge you get in that spot. If you don't have a charge, leave it blank. You don't have to write 0, 0 plus or 0 minus or anything like that. Just leave it. Don't put a charge there. Okay. So fill in the table with the information that is shown there. Okay. You will need to find a periodic table. So go back to P table. And then you do want to write out the name in the blanks where it says element name. I'll give you 5 minutes to do it. We'll see you in a bit. 1 or 2 more minutes, we'll go over the answers. All right, let's see what we got here. So we're going to need p-table. I have a periodic table here in front of me, so I'm going to use that. I don't want to use this pen, though. There we go. All right, so looking up titanium on the periodic table, titanium's element number 22, which means that it must have 22 protons. So we'll just fill that in. And then we've got this information so far. If there are 22 protons and 24 neutrons, the mass number would be 46, because I add these two together. I'll put an A there to just show that. And then the charge would be these two related to each other, 22 positive charge and 20 negative charge. Overall, the charge would be positive 2. And I'll just write that like charge. We're going to do the same sort of strategy, so I'm not going to keep doing this and that over and over and over. All right. For the next one, we have to work a little bit backwards, so we'll start the easy thing. So this is obviously bromine. How many protons does it have? Well, that's listed right here. It's 35. You could also just look at the periodic table. 35 plus 46 should equal 81, and it does. And then number of electrons. Well, I have a charge of negative 2, so I need to have 2 more electrons than protons. So we'll do that. There you go. The next one, I just have a bunch of numbers here, so I need to look up what element this is. Well, it has 6 protons, so according to the periodic table, that is carbon. Its mass number would be 13 because I have 6 protons and 7 neutrons. And its charge would be, I have 2 more electrons than protons. So there you go. We'll follow the same strategy down here. So for this ion, 82 protons. How many neutrons would I have? Well, I would have 82 plus something equals 205. So that would be 811. Nope, I can't do math. Sorry, hold on. Five minus 2 is 3. There we go. 20 minus 8. There we go. 123. I think that's right. Someone can check my math. Okay. And then I have 4 fewer electrons than protons, so that must be 78. And then same thing for this one down here. So 44. I have 94 protons plus neutrons, so this must be 50. Because 44 plus 50 is 94. And I have 3 fewer electrons than protons. And, oh, I got to write the name in here, too. There you go. So that's how we write isotopic notation symbols and relate the concept of charge to all the things that we learned today. Let me know if you have any questions. All right, so the last bit of this section is going to actually involve a lot of algebra. I want to check something real quick just to see, is this something I can do in 10 minutes? Not really. Actually, this is probably going to take like 30 to 40 minutes to fully go over. Can we talk about isotopes real quick? Yeah, we could start this. We won't do the math part of this yet. We'll just talk about what isotopes are. And that'll be good enough for today. All right, so let's talk about what isotopes are, because earlier on in the unit, I mentioned that all atoms are chemically identical, but they're not physically identical. And there must be some entity in here that doesn't affect chemistry in any way, but affects its physical nature. And that thing is the neutron. The neutron doesn't have a charge, so it's not going to influence the chemistry. It's not going to change the number of electrons. It's not going to change the number of protons or anything weird like that. But what it does do is it adds mass. And so you get different atoms that have the same reactivity, but have different masses, and so they react at different speeds. It'd be like playing baseball, but if you had a bin full of baseballs and 5% of them weighed twice as much. Like, they're otherwise functionally the same. They're the same shape, they're the same texture. But if you threw a ball that was twice as heavy, it would be twice as hard. It wouldn't go anywhere near as fast. And when you hit it, it wouldn't go anywhere near as far. So the result would be different, even though the appearance of the result, you throw the ball and you hit it and play baseball, would be functionally equivalent. Isotopes, it's sort of the same thing. We don't really care so much about their differences in mass because the differences in mass are pretty tiny most of the time. With some isotopes, it's actually significantly different. For example, hydrogen and deuterium. Hydrogen is just one proton and an electron, that's it. Deuterium sticks an extra neutron in there. And that more or less doubles the weight of the atom, and that can actually be significant. But for all these other isotopes that we're going to talk about, the weights are going to be very, very, very relatively similar. And so we won't super care about them very much. But there is one important consequence, and we'll talk about that today. So I'm going to put 3 things on the board here. They're all boron. They all have the same number of protons, and they all have the same number of electrons because they're all neutral. So they'll all react like boron would, however that is. We don't really care about that. But you'll notice that their mass numbers are very different. And so if I make a little table here, so if I go protons, electrons, neutrons, then they all have 5 protons, and they all have 5 electrons. That's not very exciting. But if I look at the number of neutrons in here, the mass number is 10, so there must be 5 here. This one, the mass number is 11, so there must be 6 here, because these two, again, have to add up to be the mass number. And so there's obviously a difference in between these species. We're going to call any collection of atoms, when compared against each other, isotopes if they meet this criterion. So I'm looking at A here. And there's our criterion. Same Z, different A. Two atoms are isotopes of one another if they meet that condition. Their atomic number is the same, but their mass number is different. Now, how many isotopes can exist? You can have any combination of protons and neutrons that you want to. Some will be more stable than others. I think I mentioned earlier, if you have too few neutrons, the protons repel and the atom will decay. If you have too many neutrons, the neutrons don't stick, and then they either turn into protons or they decay off themselves. So This is going to lead us into a discussion, which we're going to continue on whatever the next class is. Monday next week? Monday next week. Sorry, my offset schedule, I get so confused on when we actually meet. We're going to talk a lot about which isotopes are stable and naturally occurring versus which isotopes are synthetic. What that means for calculating the average mass. Like, I just went to the boron bin and I scooped out a random assortment of boron. What would I actually find in there? That's where we're going to go with this discussion here. Now, with isotopes, you often see names written like this. So, for instance, I would call this one boron 12. And this number right here is the mass number of the isotope. You may have heard of this with nuclear power, so things like uranium-238 or uranium-235, which is the fissile one. 235 is the good one. You use that for nuclear power in your factory in Factorio. And uranium-238 is the crappy one. You throw in a bin and eventually make bullets out of it or something for the biters. If you haven't played Factorio, you should. It's fun. But suffice it to say that this notation comes up a lot in various like science fiction or even like real world media. If there's a nuclear event, like when Fukushima had a meltdown due to the tsunami and the earthquake, the spillage of radioactive material that went in the Pacific Ocean caused concerns because a particular isotope of iodine, I think it's iodine-131, is very radioactive. And iodine is a very important nutrient for people because it regulates your thyroid. And so you would have to drink iodine supplements to saturate your thyroid with non-radioactive iodine so that you wouldn't absorb the radioactive iodine if you happen to get it in your diet or whatever. So those are just instances of why we would care about specific isotopes and this nomenclature and how it comes up. Now, again, for naturally occurring isotopes, most elements have like 1 or 2 isotopes that are common. Some have lots of them. Oh, Factorio with an O on the end. Yeah, not Factoria. I forgot that we actually have a city called that. No, Factorio. I like playing these games where you build a factory. Like, they're just fun to me. Trying to make like a design that works. I'm not efficient at all. My factories look like spaghetti with conveyor belts going all over the damn place. But yeah, I need to start playing Satisfactory again because that was also a really good game. I'm playing Dyson Sphere Program right now, and it's also really good. Naturally occurring isotopes vary depending on the element. There's really no rhyme or reason as to why certain elements have 2 isotopes, certain elements have 1, certain elements have 10. Some don't have any at all. For instance, if you look at the periodic table and you look at technetium, number 43, there are no stable isotopes of technetium. If you go digging in the earth, you will never find a single atom of technetium because it doesn't naturally occur. It's too radioactive. It all decays away. Same thing with promethium. That's number 60-something, 61. There just isn't any of it for some reason. I don't actually know the physics behind that. But for some reason, no combination of 43 protons or 61 protons and whatever number of neutrons yields something stable. And so those elements are synthetic. You have to make them. Naturally occurring things are buried in the earth. Now, naturally occurring things can still be radioactive. For example, uranium-235 and uranium-238 are radioactive. There's tons of uranium-238 in the Earth, and it is mildly radioactive. It has a half-life of 4 billion years. What that means is that if I had a ton of uranium, after 4 billion years, half of that would have irradiated away and become some other element, probably lead or thorium or something like that. Now, there is a lot of uranium in the Earth, and its half-life is very, 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 very long. The Earth's age is roughly on the order of the half-life of uranium. And so, Since only half of it would decay in that time, the other half still is around, and we can mine it up, and we can make it into things like nuclear fuel, or you can use it for like armor plating because it's super dense, or, and this is not a good idea, and yet we've done it, you can use it for glaze and coloring food. Uh, 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 what's the word that I wanted to say plates, but I said food, and I was trying to segue. So, if you ever heard of what is it called? Oh, I'm gonna have to look this up because we're done for the day. This is where we're gonna stop. But Fiestaware, that's what it is. If you look up Fiestaware, Fiestaware was this brightly colored. Well, the glowing clock. Sorry, the glowing clocks is actually radium. But specifically for uranium, if you look up Fiestaware, specifically like the bright orange color, the glaze that was used and to color that ceramic earthenware was a uranium oxide, and it is mildly radioactive. And if you take a Geiger counter to it, it goes off like crazy. And yet people would eat stuff on this. Now you might think, oh, it's glazed, it's no big deal. But if you put something acidic on it, such as, like, say, spaghetti sauce is lightly acidic, because tomatoes have acid in them, their pH is less than 7, that will slowly, over time, dissolve the glaze, and so you'd get uranium in your meal. It's a very, very, very trace amount of it, but that could be really bad, obviously, because you don't want uranium in your body irradiating away. So, synthetic isotopes have very short half-lives compared to naturally occurring isotopes, but this slide is not intended to say, oh, it's natural, it's safe, it's not radioactive. Anything synthetic will be radioactive. I really need to just drink more water here. So when we come back, and I think that's more or less where I wanted to stop here. We already... Wow, I don't know what's going on with my throat. Hold on. Excuse me. We already talked about how to describe different atoms by using this isotopic hyphenated notation. So you can see some examples of that on the screen here. But you've probably heard of this notation before, and also different isotopes, and maybe even Fiestaware. Don't eat off of Fiestaware. Not the orange one, anyway. I think the other colors are safe. All right. And I don't really care about isobars, so we'll just talk about it next time. I do want to thank everyone for coming out to the lecture. I wish we could talk more about radioactive stuff, because that's fun. Unfortunately, it doesn't really fit into this class. I try and squeeze it in when I can, though. Things to note. Don't forget, quiz number 2 is tonight. I did check the last call email. Did go out. Make sure you finish it. Quiz number 3 is due next week. There's a lab going out. Oh, there's a question from last class. Yeah, what's up? We have a second. I can definitely answer it. Let me actually put that on the screen here, so that future students watching this video can see what question this is. So, what's your question? I'll just chug more water here. Is carbonation a physical process? That's actually a hard question to answer in the context of this class, because it's kind of both. So, one, carbonation is physical because you're mixing CO2 and water. However, when you carbonate something, what you actually do with water is carbon dioxide and water react to form carbonic acid, which is why when you drink something carbonated, it tastes a little bit tart. So it's kind of a weird gray area where adding CO2 to something could be both. Now, for the purposes of this class, the answer I would expect, if this was a question I asked you, would be physical, because you don't know that H2O plus CO2 makes carbonic acid. Or presumably you don't. However, the internet does, so If that's a question on the quiz, let me know, because that shouldn't be. If it's a question on a worksheet, though, I could be asking that to you just to get you to think about it. All right. Hopefully that answers your question. Yeah, that's all I got. So make sure you get in all the things by the deadline. We're 4 weeks down, only 6 weeks to go. It's going to go pretty quick from here. So have a wonderful weekend. I will see you next week. We'll finish up Unit 7 and 8, and then we'll get ready for a midterm.